Now we are going to study about NOR-based R-S Latch. This is nothing complex. Okay, this is nothing complex because if you watch the last video, you will understand how R-S Latch works. Now we are just going to draw NOR gates. Okay, NOR gates in a specific way so that it works as R-S Latch. That's it. Nothing serious. But that's it. There is a small thing I need to teach you: active high. An idea called active high. What does active high do? Well, active high means the truth table or the logic circuit works for the inputs when the inputs are 1. It is designed when inputs are equals to 1. What do I mean by this? Well, let's take a combinational system that is said as x is equals to a plus bc. Okay, a plus bc. Now, we know what this means is when a is equals to 1 or b and c are equals to 1, x will be equals to 1. Okay, instead of saying when when a is equals to 0 or b and c are equals to 0, x is equals to 0, we say x is equals to 1 when a is equals to 1 or b and c are equals to 1. We are talking about 1 rather than 0. That is what we call the active high. Active high. So the system works when the inputs are considered high or 1. Okay, so here in the R-S Latch, we have reset and set inputs, right? We have reset and set inputs. So when we are talking about reset and set inputs, we are talking when they are equals to 1. When reset is 1 or set is 1, the system will work as intended. That is the speciality for NOR-based R-S Latch. We will be studying about NAND-based, that will be active low. I'll teach you in that video, but for now you have to know what active high means. Active high means when the inputs are 1, the output is considered 1. Okay, so what does this look like in a truth table? Well, if we draw A, B, C and X, we need a plus bc, so it could be 0 1 1 or 1 0 1 1 1 0 or 1 1 1, or we can also have 1 0 0. Yeah, that's all. For all these input combination, x will be equals to 1. That's the idea. Okay, that's the idea. Similarly, for R-S Latch also we have a truth table, and based on that we are going to build the NOR gates based R-S Latch. So let's come up with the truth table that we studied already in the last class. We have Q, we have Q bar, and operation. Let's just leave the operation out for now because operation is practical implication. Okay, that's implication. Okay, we don't have to consider that for drawing the diagram. We just need the truth table. So we know we have R is equal to 0 0 1 1, and then S is equals to 0 1 0 1, and we know Q should be previous state. Okay, Q should be no changes. Okay, Q should be in the previous state, which means Q bar is also in the previous state. Okay, let me explain this specific term. We know Q has two states. Okay, we know Q has either Q is equals to 0 or Q is equals to 1, which is Q now, which is derived from Q previous. It is derived from Q previous. We know at the exact specific time it's called as Q now. Right before this exact specific time is called Q previous. Okay, and when R is equals to 0 and S is equals to 0, Q have to keep its original state or the initial previous state. So if Q previous was 0, Q now will also be 0. If Q previous was 1, Q now will also be 1. It will keep being 0 or keep being 1. That's the idea. Okay, what if the set operation happens? Well, when R is equals to 0 and S is equals to 1, Q should become 1. Since Q is 1, Q bar should be 0. Similarly, when reset is equals to 1 and S is equals to 0, then Q should become 0. Since Q is 0, Q bar will be 1, and we know these two are invalid. These two are invalid. When R is equals to 1 and S is equals to 1, it can't happen. It is forbidden. It is invalid. Okay, that's the idea. So if I want to explain further on this condition, the second combination, this is the first combination that we studied already. Okay, and now we have the second combination. Let's talk about the second combination also. It doesn't matter what Q previous was. Okay, It doesn't matter what q previous was. It could be 0 or it could be 1. When you are setting, okay, when you are setting or r is equals to 0 and s is equals to 1, q now has to become 1. That's the idea. It has to change. It has to change. Similarly, for the third combination, okay, for the third combination, q previous could be anything. It could be 0 or it could be 1. Q previous could be 0 or q previous could be 1. But q now has to become 0. That's the idea. Because we are resetting. We are resetting. Here we are setting. That's all. So we have the truth table. Okay. Now we have to draw the NOR gates based on this. We have learned how to draw combinational circuits. Okay. We have learned to draw combinational circuits. That is not an issue. But here this is sequential circuit. So it's a little bit complicated. Okay. Since we are beginners for sequential circuits, we are normally given the circuit equation. So Q is equals to, they are giving us R plus Q bar whole thing bar. Okay. Similarly, Q bar is given as S plus Q whole thing bar. Very straightforward. Okay, very straightforward. You can actually think of it. So if we have Q bar and R, we have to send through one NOR gate. If we have S and Q, we have to send it through one NOR gate. Okay, you don't have to create Q bar specifically. Why? Q bar is also an output. We are going to feed it back. So we will need only two NOR gates. There is a NOR gate here entirely. Here there is a NOR gate entirely. Okay, so let's draw it. R is there. S is there. We have to send R through a NOR gate first. So let me draw a beautiful, beautiful NOR gate. Okay. And R is related with Q. Okay. R is related with Q. So here we will put the Q. And similarly, here we have S. And then we know S is related with Q bar. So let's draw that also. Let's draw this here. And this is Q bar. And Q bar is sent through a NOR gate along with R to come up with Q. And similarly, Q is sent through a NOR gate along with S to come up with, oh no, yeah, sent through another NOR gate to come up with Q bar. So here you will know Q is equals to, this is Q bar. This is the feedback circuit line. So Q is equals to R plus Q bar whole thing bar. And then here we have Q bar. So it will be equals to S plus Q whole thing bar. Why? This is Q. That's it. This is the R-S latch. The thing that's behind the block diagram. Okay. The thing that's behind the block diagram. So if you draw a dotted block here, this is what was hiding for all this time. Okay, now let's understand how this works. Okay, let's understand how this works. We know we have R and then S, and then we have Q, which is given as R plus Q bar whole thing bar, and then we have Q bar, which is equals to S plus Q whole thing bar. Now you have to be very careful about one thing. Okay, let's put the combinations also 0 0 1 1 0 1 0 1. Now this is the idea. Okay, when we say Q bar here or when we say Q here, that is not Q bar now or Q now. That is Q bar previous, Q previous. Okay, that is Q bar previous and Q previous. Here the Q bar is actually the opposite of Q previous. Okay, opposite of Q previous. We don't know what Q previous is. Okay, we don't know what Q previous is, but the logic circuit, the system that we have come up with, works for any Q previous. Okay, that's how it's going to work. Okay, so let's study about the first combination where R is equals to 0. First combination where R is equals to 0 and S is equals to 0. Okay, what is the expected output? Well, Q has to be Q now has to be Q previous. Q now has to be Q previous, and Q bar now should be equals to Q bar previous. That's the expected outcome. That's the expected outcome. Now we know the equation for Q is equals to r plus q bar previous, q bar previous whole thing bar. Okay, now tell me, okay, uh, now tell me what is this equals to. Okay, what is this equals to? Let's simplify this. R plus q bar previous, so it can be given as 0 plus q bar previous. I'm just going to use pre here after, it's a long word. Okay, then we have 0 plus q bar previous, 0 plus q bar previous whole thing bar. That's what we have. So that is q bar previous over bar, so that is equals to q previous. So we have now achieved q now is equals to q previous. That's it. Similarly, we have the q bar now, and that is given as s plus q previous whole thing bar. So that is 0 plus q previous whole thing bar. So that is equals to q previous whole thing bar. So that is q bar now. So it also works for q bar now is equals to q previous whole thing bar. That's the idea. That is the expected outcome, and it also works for all the both combinations possible. Okay, now let's go to the second combination, which is r is equals to 0 and s is equals to 1. Okay, what is the expected outcome? Well, q now should be equals to 1, and q now bar should be equals to 0. That's the idea. Before we go into this, I'm going to teach you a short circuit. Okay, I'm going to teach you a short circuiting method for NOR gates. Okay, for NOR gates, we know a plus b whole thing bar is there. For NOR gates, a plus b whole thing bar is there. If x is equals to a plus b whole thing bar, if either one of either one of a or b, okay, if a or b is equals to 1, x must be equals to 0. Okay, if a is equals to 1, then without even considering b, you can say x is equals to 0. Similarly, if b is equals to 1, you can say without even considering a, you can say x is equals to 0. Why? Well, let me teach you. X is equals to, let's say we know only a. Okay, so a is given as 1. So 1 plus b whole thing bar is equals to 1 whole thing bar, which is equals to 0. Similarly, if x is equals to a plus 1 whole thing bar, then you can say that is equals to 1 bar, because a plus 1 is equals to 1. So 1 bar is equals to 0. This is the short circuit method. Since here we have s is equals to 1, so we will first of all look at q bar only. We will look at q bar only. So we know first of all q now whole thing bar is equals to s plus q previous whole thing bar. Now we know s is equals to 1. So 1 plus q previous whole thing bar. So that is equals to 0. So q now whole thing bar is equals to 0 means, okay, q bar now whole thing bar is equals to 0 means q now has to be 1. Q now has to be 1 because these two are inverse. So we can say q now is equals to bar of q now whole thing bar. And we know q now whole thing bar is equals to 0. So 0 bar is equals to 1. That's the idea. That's the idea. You can't come like this. Okay. You can't come like this. By using both equations, you can't find for second one. Because if you try that, it will be 0 plus q previous whole thing bar. So you'll need to know what is q previous, which you don't. So q now 1 will be equals to 1. That's the idea. Okay. Similarly, we go to the third idea, third combination, where r is equals to 1, s is equals to 0. Okay, so here before we move there, I'll just write this down for you. It actually achieves the our expected outcome. Q now is equals to 1 and q now whole thing bar is equals to 0. Okay, so similarly here we need Q now is equals to 0 and Q now whole thing bar equals to 1. That is very important. Okay, so how can we do this? Well, we will go for Q this time because we know Q is equals to R plus Q bar whole thing bar, and this is Q bar previous, this is Q now, and R is equals to 1, that is Q previous whole thing bar, so that is equals to 1 whole thing bar, so that is equals to 0. Okay, Q now is equals to 0, and we can say Q now whole thing bar is equals to Q now over bar, and we know Q now is equals to 0, so 0 bar will be equals to 1. So we know Q now whole thing bar is equals to 1. The expected outcomes are reached. The expected outcomes are reached. So this is how you are going to work with this. And for fourth one, it doesn't work. I'll teach you why through the circuits also, why it is invalid. So we have R is equals to 1 and S is equals to 1. If you put the equation for Q now, okay, if you put the equation for Q now, it will look like R plus Q previous whole thing bar, and since R is equals to 1, Q now will be 0. Okay, Q now will be 0. Then, okay, then you normally know Q now whole thing bar is equals to 1. You already know it should be Q now whole thing bar should be equals to 1. But if I apply this equation, okay, Q now whole thing bar, well, we know it is equals to S plus Q previous whole thing bar. Okay, Q previous whole thing bar. But since S is also equals to 1, Q now whole thing bar will also be equals to 0, which means according to this, Q now should be equals to 1. These do not go with each other. How can the same output have two states at the same time? That is not digital logic. According to digital logic, a specific output can only be one state at a time. One state at a time. Okay, at a point of time. Here they are taking both. So that is not possible. So that is why it is considered as invalid or forbidden. So there is a safety measure to not allow this to happen. Okay, so now you know how NOR-based R-S Latch works. Okay, now you know how NOR-based R-S Latch works. Quick summary. Okay, what you need to know is this circuit. Okay, you should be able to draw the circuit based on the equations that you have, and then you should be able to analyze this. Okay, but please be careful. This has nothing to do with practical implications. Okay, there won't be a question that requires this for practical implication. Okay, practical implication 1 I have taught you in the first video itself. If you need to know how to work with graphs or the questions related to graphs, go to the first video, not this one. This is what's happening behind the scenes. Okay, what happens behind the scenes. That's it. In the next video, I'll teach you how you can work with NAND gates based R-S Latch. Don't forget to watch that video also. Thank you for watching the video on NOR-based R-S Latch. I hope you found this video helpful, and if you found this video helpful, don't forget to like, share and subscribe for more lessons. I'll meet you in the next video. Until then, keep learning and stay curious.